Sorry, I just started recording. Now, Yancy, go ahead.
Okay. Hi, everyone. Sorry I couldn't be there. I had a little bit of an eye emergency this morning, but it's my great pleasure to introduce Lucy Steffes. Lucy Steffes is one of our NSF graduate research fellows in the department, and she's a second-year graduate student here at U of A. And she's going to give you an update on the project she's been working on, one of actually multiple projects she's been working on today, talking about the velocity structure in the central part of the Taurus Molecular Cloud. So please take it away, Lucy.
Thanks, Yancy. So we'll get right into this. Let's see. Okay, so here's a picture of the Taurus Molecular Cloud. This picture was taken as part of the Herschel Gold Belt survey, and I think it's a really good illustration of how much complexity there is in even a relatively close by and low mass molecular cloud. One of the advantages we have with this project is that Taurus is close by. It's only about 140 parsecs away. So we're able to get really good resolution compared to other further away molecular clouds with the same instruments. So just as a brief outline, we'll start by talking about how we identify and separate multiple velocity structures within this molecular cloud. Then we'll talk about filaments, all things filaments, from identifying and building them, comparing them, and measuring velocity gradients along these filaments. And then we'll end by talking about cores, core rotation, and gradients in those, and along with some of the chemistry that's going on inside of it. So in this talk, it'll be really broken up into two sections. The first one with identifying the structures and filaments will be mostly talking about the methods. And then the second section will be more talking about the analysis that we can get into once we've done these methods. Okay, so a bit of background. Starless cores, which will be a major aspect of this talk, are the incipient phase of star formation, and they're the fundamental building blocks of stars. So they're the first stepping stone that we have from going from molecular clouds to getting stars. Some of the questions that we would like to know is, how do starless cores form in molecular clouds? How do the filaments that they largely reside in grow and evolve? And how do these two things grow and evolve together? We'd like to know this because currently the main ideas is illustrated over here on the right. So we have these filaments with cores inside of them, and we think that gas flows along these filaments to accrete onto the cores, and eventually through some somewhat debated processes end up with a protostar that may have a disk, an envelope around it, and jets. But how does gas get onto these filaments in the first place? Does it accrete closer to the cores? Does it accrete onto the filaments and create densities there? So that's one of the things that this project will aim to probe. We'd like to look at how gas goes from large to small scales, and also understand the difference between the gas kinematics inside of these cores and in the gas surrounding them. We'd also like to know the primary contributors to these gas flows. So I should mention, and I've mentioned this briefly before, that Taurus is generally a low mass star-forming cloud. So it forms mostly low mass protostars, which means that something like gravity can have a slightly lower contribution to these gas flows. So if we take gravity potentially out of the picture, then what else may be contributing to these gas flows? Could it be pressure, magnetic fields, turbulence, or something else? Okay, so going back to the Taurus molecular cloud, we have a few different images of Taurus. We can see here in the optical these dark, very dusty clouds that are attenuating a lot of the optical light from the stars behind it. That's originally how Taurus was observed before we had the ability to access the rest of the electromagnetic spectrum. And in contrast to these optical images, we can see that these molecular structures really start to light up in parts of the spectrum like the infrared, where we can see these filaments kind of around here down this main backbone, and we can see these class 0 and class 1 protostars start to turn on. But when we look in the radio with the CO, where we have a lot more information about the velocity structure, things get really complicated. There's a lot of this more intermediate velocity from the green, but there's also red and blue shifted gas that all kind of mix together. And today, I'll walk you through how we start to detangle this. So in this data set, instead of using a line in the radio like CO, we'll be using ammonia, which is shown here, NH3. So this data set was originally observed using the Green Bank telescope to observe both the 1,1 and 2,2 inversion transitions of ammonia, which is an intermediate density gas tracer. And so we'll be tracing mostly higher density environments than what is able to be done with CO. So Youngmin Zhao, who originally conducted these observations, one of Yancey's former grad students, as part of his analysis, he identified these 39 cores, which are indicated with the X's, through a dendrogram analysis using CSAR. But you'll notice that in some places where there is gas, like in here, gas is lighting up, but there's no cores identified. And part of the reason why Youngmin couldn't go further with his analysis in those regions is because there's a lot of overlapping velocity components where you have two gas clouds that are along the same line of sight, but at different velocities. And he didn't have as much of a way of breaking those apart and identifying the structures to be able to analyze them. But we can start to solve this problem now. So when I first started this project about 1.5 years ago, I started by working with Nested, which was developed by another one of Yancey's former grad students, Brian Svoboda at NRAO. So Nested uses a combination of Bayesian and MCMC routines to first identify the number of velocity components at each pixel throughout this entire map. So I show the locations where the Bayes factor indicates that there should be 2 velocity components in yellow, and then 1 velocity component is shown in that red. There's a lot of other gas that was mapped, for example, around the edges of this section that were too low signal to noise ratio to clearly identify any velocity components. So those have 0 and are therefore shown in black. So for the purposes of this talk, we'll only be looking at the gas that has either 1 or 2 identified components. So let's zoom in on one of these regions. This is the B213 region. We can see that there's a good mix of 1 and 2 component structures. So let's zoom in to just 1 pixel, and we can look at the spectrum on top, where you can see the main peak in the middle, and then 4 groups of hyperfine structure, 2 on the left, 2 on the right. Now on the bottom, these are showing the posterior distributions. So a probability distribution function of the velocity for each of these 2 components right here. So the higher intensity component, which is at a slightly redder velocity, is a lot better constrained. It's higher signal to noise. We can much more clearly identify those 4 hyperfine groups. But the bluer velocity clump there is less well constrained. So the posterior distribution peaks at a lower probability, and it's a little bit wider because it's at a lower intensity and we can't see the hyperfine structure from the noise quite as well. So When separating these structures, the key thing that I'd like to ask is how can I break apart these structures, which oftentimes do overlap in velocity space and have complex gradients, shapes, and there's a lack of a clear identification. So on this slide, I've identified them as being component 1 and component 2. But what happens when we shift from here to down here to where there's only one component? Well, in this redder part of the map, everything is labeled as being component 1, regardless of if the structure that it's a part of is otherwise identified as being component 2, which made it a tricky problem to solve. But the way that I've gone about doing this is by using this code called ACORNs, which stands for agglomerative clustering for organizing nested structures. So the inputs for each component at each pixel, so for pixels that have 2 velocity components, you put in 2 inputs, include the coordinates, the integrated intensity for that component, the velocity for that component, the line width, the RMS of the spectra at that pixel. So in cases where there's 2 components, you just put in the same RMS twice. And the errors on all of these values except for the RMS and the coordinates. So how it works. Instead of putting in the entire spectrum for the entire cube, and you instead put in the discrete information. So it made it a lot easier to be able to put in each of these inputs for each component at each pixel. And then it does a hierarchical agglomerative clustering and then a dendrogram analysis to identify structures based on the input parameters that I give it. So along with each of those discrete data points that I put in, I have to set some parameters for this dendrogram analysis. So I set a minimum radius of any given structure to being 3 pixels, which is half of a beam size for the KFPA on the Green Bank telescope. So that's the limit for Nyquist sampling for these observations. And then I put in the original velocity resolution of these spectra. With NestFit, we're able to get better velocity resolution, but for the purposes of these structures, I wanted to stick with the original spectral and velocity resolution. And then in order for it to consider a point that, or one of these data points that I gave it, it needed to be at least twice the RMS. The line width I chose as being a median line width for the entire cube. And I gave it minimal relaxation parameters. Here's going to be an example of what that identification of structures looks like. And we'll do this specifically in a smaller region in the B10 region. So here we see a position velocity cube that ACORNs was able to output. So each of these colors is a different structure. So you can see a more extended green structure and then some slightly overlapping yellow and red here. So some of the key features that I want to point out is that there is this somewhat overlapping structure, which corresponds with the main core containing region in D10 located here. Then you also see that this one isolated core, which is here, is at a more red velocity, but it's completely surrounded by bluer velocity gas. When we look at this in 2 dimensions, so when we look at those velocities and map them, with each of the cores identified by an X here, we can see how that was all looking. So here are the 2 main overlapping structures, which were those yellow and red. This one was yellow and this one was red. We can see that they weren't quite overlapping as much as we may have thought from the PPV cube, But in the middle here is where most of that overlap happens. The velocities are distinct enough that we don't want to accidentally analyze the velocity gradients between these two structures, which would artificially give us very high velocity gradients. And here we are making an assumption that these two structures, so this blue and this red, are not interacting with each other. One of the other things that we can see from this map is this gray map, where I kind of just use that as a catch-all. So everything else that didn't fit into these main other structures. So a lot of these line up pretty well with where we see core peaks, which I think mostly come from having line asymmetries and high densities. Anytime there's a line asymmetry from some amount of collapse or motion within the core, NestFit oftentimes goes and identifies that as being a secondary component rather than having a way of identifying it as a line asymmetry. So as another example that gets a bit more complex, we can go down here to the B213 and B211 regions. I've combined these two for the rest of this analysis into just being one mega region, because as we'll see, there's not a clear way of drawing a line right in between them when we have the velocity information, which was not available when these regions were first being identified by Barnard. Okay, so zooming in, we see that this region gets a lot more complex. There's a lot more clouds identified. And roughly in here-ish is where that line would have been drawn, but you can see that there's an overlap. This magenta region that I'm pointing at was previously the only region in B211 that was able to be analyzed for core identification because it's at such a different velocity and it's mostly one single component velocity there. We've also been calling that the scorpion tail because I feel like it goes up like a scorpion. Then over here, as I previously pointed out, we can see the overlapping structures at that border between B211 and B213. So that's why I've combined these two regions into just being one for the purpose of this analysis. Then we can see some of the smaller clumps or cores that mostly seem to come from the cores, the line asymmetries in the cores, especially since a few of those down here in B213 are known class 0 or class 1 protostars that are still fully embedded within the ammonia gas. But then we also see down here in this green and purple that these two neighboring structures were separated, perhaps due to some differences in velocity, or more likely because they seem to be at pretty similar velocities due to differences in their line widths. And we can see that more clearly here in the purple and blue on top. They'll come back to in just a minute. But as I pointed out on the previous slide, there's these additional components that come from the line asymmetries, often at high densities. But in the gray, because there is so much going on here, it became a bit more than my catch-all for the line asymmetries, and also includes other structures that were often overlapping with the bluer gas on top. So we see that in this mostly white here and this large gray region. So those are some examples of other structures that I'll be analyzing for cores and filaments this summer. Then, as I pointed out, I used these different color bars to show the differences between these two different structures that do sit right next to each other, with the main border being this kind of squiggly line right around here. And then finally, all of the contours are showing the borders of where there was either 1 or 2 velocity components and 0. So if it's outside of the black contours, that's where there was 0 components identified. But if gas is separated by contours, that often means that it was identified to be 2 different structures by acorns. Okay, moving into filament identification. So my key question here is, how can I identify filaments now in the position velocity space, and how do they differ from filaments identified through other tracers, these being dust and other gas tracers? So the code that I've used for this part has been the Crispy code put together by Mike Chen in 2020. And it stands for Computational Ridge Identification with SCMS for Python. And gotta love a nested acronym. SCMS stands for Subspace Constrained Mean Shift, which is just a ridge identification algorithm. But one of the benefits of using Crispy as opposed to another filament identification code like FillFinder or Disperse is that not only can it be used for an n-dimensional cube, in this case a 3-dimensional cube, but it only has 2 input parameters. So these 2 are a smoothing parameter where you put in spatially how much you'd like to smooth over. So in this case, I'm again using 3 pixels for that Nyquist sampling of half a beam size. And then a minimum density threshold, which is, in this case, going to be a minimum intensity threshold. Because rather than using the raw ammonia spectra, I collapsed this down into being a single Gaussian that has the same velocity and line width and the same total integrated intensity. So then I can put in some minimum intensity threshold, which I believe I generally put in 1.5. So if the total Gaussian falls below the 1.5 Kelvin mark, then it doesn't consider it for looking for filaments. You can also see in this particular spectrum, there's a bit of a shoulder here, right to the side. And that's because this is from a pixel that has 2 velocity components. So in the cases where there was 2 velocity components, I put in 2 Gaussians that each one of those 2 Gaussians have the same velocity, line width, and integrated intensity of their respective components. So now we can see what those outputs from Crispy look like. It's a bit tricky to see on this projector screen, but I've pointed out some of those filaments, which are now shown in red. So you can see a few of them down here, and then a few mostly on the top, and one down here. So there is a huge variance in the length of the filaments and also in the number of cores in each filament. Some of them have no cores, and the one on top, which we'll see in the next slide a little bit better, has 4 cores. Some of these filaments may also be to these smaller scale fluctuations that do start to get included because I wanted to play around a little bit with my intensity threshold. So by making it a little bit too high, you're no longer including the full filament. But if you make it too low, you do start to include some things that are perhaps a bit more systematic, but that's something that I'm continuing to look into. So here we can see these filaments plotted now in 2 dimensions, with each filament being shown on the respective velocity structure. So you can see that there are some small gaps between some of these filaments, especially on the red side. So there's a small gap in the navy blue filament here. There's also a small one here. Now, some of these could come from shearing from gas rotating in cores, or they could just be crossing a gap where there is lower signal to noise ratio gas due to lower density gas, oftentimes in between these cores. But there are also these small filaments in non-core containing structures, so not even filaments that don't have cores, but filaments in structures that also don't have cores, which are mostly this pretty low density blue gas here, and these little clumps of slightly redder gas that are not necessarily affiliated with any cores. So moving on to this comparison of filaments. So I started with these C18O filaments, so an isotopolog of CO that is able to get us to slightly higher densities than CO, so, because this 18 oxygen is not nearly as abundant as 16 oxygen, so we're able to have lower optical depths. But we can see the filaments in red that Alvaro Hikar identified through a friends of friends analysis after observing C18O with the 5 Colleges Consortium Radio Observatory. Then overlaid on top of that is, in gold, is these dust filaments that the dust observations come from the Herschel-Gould Belt Survey, and they were identified using the disperse code, which is originally a cosmology code. But you can see that there are some similarities and some differences. One of these differences does come from the fact that these dust observations include no information about the velocity, so the dust can sometimes make some interesting choices about connected structures, where when we have the velocity information, we've recognized that they're not connected because they're at 2 different velocities. But with these two, we can see that they do sometimes cover different and more extended structure. And this is especially in comparison to the ammonia filaments, where they cover the least extended structure. As I mentioned at the beginning of the talk, ammonia is generally an intermediate to high density gas tracer. So it'll be a lot more clumped up compared to the CO and the dust, which will be more extended in structure. But to help with this, let's zoom in again to the B10 region, where I changed the ammonia color to be black to help it stand out a little bit more. So hopefully against the brighter backdrop of the high intensity gas, you'll be able to see it. But in general, we see that the shapes of the filaments are roughly the same, especially along these main core containing filaments, which I've pointed out here. So this one on top, this down here, and this more vertical one. But we do see some differences in the filaments that are likely due to the different densities that these tracers exist in, and are most sensitive to, and also the signal-to-noise ratio of some of these observations. Some of these differences are pointed out here, where in the dust, we do connect this isolated core to the rest of the B10 structure. In the dust, we also see these little filaments that come and cross between the redder filament up here and the bluer one down here. And we see that in some of the tracers, mostly the dust, we fully connect this vertical filament, where in the gas that doesn't necessarily happen. Some of these differences, though, could be due to the different methods used to identify each filament. As I mentioned, each one of these types of filaments were also identified through a different method and through different codes. Okay, getting into the kinematics. So, a few definitions before we fully get into the analysis. So I've used differential geometry to do most of this gradient analysis, which involves first calculating a differential one form, which is a vector field that we use to tell us how to measure another vector field. So then this vector field is, for example, taking the gradient of a map of some parameter. In this case, it'll be taking the gradient of a velocity map. Then when we project this vector field onto our differential one-form vector field, which it just involves taking a dot product at each pixel, it gives us a scalar field that tells us about the quantity that we're trying to measure in a given direction. So this will make more sense with some visuals that are specifically from this project. So this is a distance transform. What I did, and you may recognize some of the shapes, is I took each of those filaments that I identified using crispy with ammonia, and at each pixel, I looked to see how far away the closest filament was, and then put those numbers in. So it's brightest right along the ridges of each of those filaments and then tapers off. Now, in the actual analysis, I did not put all of the distance transforms for the filaments all together, because in regions, for example, like B211, the filaments are all too close together, where sometimes when you're trying to analyze this filament, you may be a little bit closer to a different filament, which could make some of your differential one forms a little bit confusing. Now, these differential one forms are shown here. So this is zoomed into one of these smaller filaments. It's also in B10. And we see in bright yellow the ridge of the filament. Now, the differential one forms are the gradient of those distance transforms. So for the perpendicular differential one form, we see that all the vectors are pointing inwards towards that filament. Now for the parallel differential one form, I rotated each of those vectors by 90 degrees so that way they flow around the outside. Now you'll notice, especially if you're able to zoom in a little bit, that on this side of the filament, they're pointing down and to the right, and on the other side, they're pointing up and to the left, so they're anti-parallel. This won't have an impact on our analysis because in all of the analysis that I do, I take the absolute value. So it'll make some of our figures occasionally look a little bit funny when I map them, but for the actual analysis beyond that, it won't matter. So now we have our vector field on the right that is the one that we're interested in, that we will use this as a tool to measure the differential one form. So here's a zoomed in map of that velocity field that was identified by acorns. So we see in blue and a little bit in red the velocities at each pixel. And overlaid on top is the two-dimensional gradient of that vector, of that velocity field. So by projecting the vectors in this map onto the vectors in this map, we get this scalar field, where green is showing where there is a match between the vector direction in the differential one form and in the velocity gradient. And purple is showing where there's a mismatch. So you can see where there's this purple just below the filament. Oops. That is where gas is continuing to mostly flow down, despite the fact that the differential one form is mostly pointing up. So, moving on from there, one of the things that I wanted to ask is, how does this perpendicular velocity gradient and also the parallel velocity gradient, which looks pretty similar to that, so we don't need to look at it, how does the magnitude of that change with respect to the distance from the filament? So how different is it when we're right on top of it versus being a little bit further away? Well, in the perpendicular direction, there's a slight increase in the perpendicular gradient on average across all of the filaments as we go to further distances from the filaments. But this is a very slight increase, and it definitely tapers off at further distances. I also go out to 12 pixels because that is 2 full beam sizes. But we do see that there is a ton of variation, especially with individual filaments. These two on the top are 2 examples where the velocity gradient in the perpendicular direction does seem to increase a little bit as we go out to further radii from the filament. Here's an example where it decreases a little bit. And then sometimes it's flat-ish, where there's a slight increase, but honestly more of a wobble. Then we can see roughly the same thing in the parallel gradients at increasing radii. There is a little bit less variation, and it's a much smaller increase. Where we don't see any that are decreasing in the parallel gradient at higher radii, just some that are a little bit more flat and some that have a slight increase. But the main thing is that there's just a lot of scatter here. And one conclusion that we can draw is when we get out further away from the filament, that tends to be where we're at lower density gas, where the integrated intensity is lower, which ultimately means that our signal to noise ratio will be lower, and often means that we don't constrain the velocity from nest fit quite as well. The other thing that we can look at is the relative contribution of each of these gradients. So on the left side of each of these plots, you'll see where the absolute value of the perpendicular gradient is larger than the absolute value of the parallel gradient for the same pixel. So just decomposing those gradients into the parallel and perpendicular directions. In general, it's pretty close to a Gaussian distribution with these lines in the middle representing all pixels that have the exact same magnitude of the parallel and perpendicular components. So the difference between them is 0. There are also long extended tails that I've truncated, which seem to mostly come from noisy pixels where the velocity is not well constrained. For example, if you have one pixel that was identified to have a pretty red velocity surrounded in a sea of pixels that are mostly blue. But we do see that there is a slight preference towards there being a higher perpendicular gradient compared to parallel, with it being about 20,000 compared to 18,000 pixels. This trend, though, is a bit stronger when we look on the individual filament scale, where above in this purple region is where the parallel gradient is dominant over perpendicular. There's 15 of those. compared to 41 filaments where the perpendicular gradient is dominant over the parallel. But we do have pretty high error bars. These error bars are showing the large scatter in the gradient values. And when I zoom in to just the core containing filaments, this trend continues where we have 5 compared to 14. You do see a decrease in the scatter because you are at higher integrated intensities. But that's also where you do start to see some of the biggest differences that are a bit more significant, where things are moving away from this dashed line at 0 a little bit. Okay, the last thing that we'll get to is looking at the kinematics of cores. So some previous analysis specifically of the physical conditions in these cores was done by yet another one of Yancey's former grad students, Samantha Schiavelli, back in 2023. And she, by doing 3D modeling of these cores in, again, B10, showed that the cores are all bound by pressure, not by gravity. And they're all very low mass. So that, as I mentioned earlier, way at the beginning is something to consider when we're looking at how the kinematics of these cores are existing. So again, here in the white axis are all of the cores. But as I pointed out previously, there are some of these regions where there are possible other cores that are at very low densities, hiding in the multi-component gas. That's part of an ongoing analysis that I've not yet completed. But with the cores that we do have already, we can see that there's a big variety in the shapes and the sizes, but we can also use the velocity information that we have to model potential core rotation. So just by looking by eye, we can see some examples of good core rotation where there's a clear axis of symmetry and a clear velocity gradient going across the core. We also see plenty of bad examples of potential rotation where there is almost no velocity gradient. Here, this one I like to think of as being kind of like a butterfly where you have a spine and 2 bluer wings. But this is how it breaks down. So we have roughly 11 cores that are good examples of potential rotation and 28 of the 39 that are likely not rotating. Some of them have very small specific angular momentum, a very weak velocity gradient, or no real axis of rotation. But what we can do is by fitting a plane to each of these in position velocity space, and then removing that to look at the residual in the underlying structure, which is shown here in pink and green. So we are limited by the velocity resolution of the posterior distributions, which is at 0.02 meters per second. And we show that Nadal cores are strong fits for rotation models, which suggests and leads us to the conclusion that core kinematics, especially at this early starless and pre-stellar core stage, are more complex than solid body rotation. We can again do this same analysis that we did earlier with the differential geometry. And then look at the distribution of the magnitudes of those gradients in a similar plot to what we did earlier. But here, these are looking at cores rather than filaments. In this case, we really don't have any strong trends between the parallel and perpendicular components, with the breakdown being 20 where the perpendicular gradient dominates and 17 where the parallel dominates. There's also 2 where there are it was exactly balanced, and they were both 0. But again, we see this large scatter. It's somewhat less than what the scatter in the gradients of the filaments was. But the cores with likely rotation, so those 11 cores that I pointed out earlier, are shown with the little stars. What's interesting here to note is that almost all of them, with the exception of these two, are where the parallel gradient dominates over the perpendicular, suggesting that these cores may be rotating with some amount of shearing within their filaments rather than rotating with the filament. So with my last few minutes, I'd like to point out some of the work of some of the undergrads who I believe just left, and look at some of the work that they've done with chemistry of cores and filaments. Yancey Shirley's group here at the University of Arizona does a ton of work looking at chemical surveys in these Herschel-Gould Belt molecular clouds. So a lot of these projects are undergrad-led. So of the projects that I've highlighted here, Maria Galloway-Spurtsma, Hannah Ambrose, Hanga Andras Latinovsky, Hannah Gruber, Lily Wilson, Grace Kaiser, Emma Vertachnik, Emily Kelly, and Jack Hoskins were all undergrads or are current undergrads here and are all leading these huge chemical surveys, largely using the Arizona radio observatories. I've also pointed out my other project that Yancey alluded to, where I'm leading this several 100-hour chemical survey in the Ophiuchus Molecular Cloud, largely focused on methanol and deuterated methanol, though other projects that I'm included in look at hydrocarbons, dense gas tracers, and other complex organics. But one of the interesting conclusions that I'd like to point out is that of Hanga Andras Latinovsky. She is a senior undergrad, so she'll be graduating, I believe, next week. And her paper will be getting submitted, I think either this week or next week. So it seems like Hanga's got a busy few weeks. But her paper, which will be coming out soon, shows that the deuteration fraction of formaldehyde, H2CO, correlates along filaments. So here the circle size, the increased circle size shows the increased deuteration fraction of HDCO compared to H2CO. And it suggests that these spines chemically evolve as a unit. So they're not only spatially and kinematically distinct from each other, but they're also chemically distinct. And this also suggests that deuteration fraction is another method of measuring core evolution. What she also shows, and she's done so many of these comparisons between the different deuteration fractions and abundances of molecules, and physical parameters. She shows that the deuteration fraction is not well correlated with density or with most of the other physical parameters, where I've shown density here. So going between them, we see pretty well correlated circle sizes. She has more mathematically rigorous techniques in her paper. But then going over here to the core central density, and the circle sizes are not well correlated at all. Okay, so some final conclusions. We see that the velocity kinematics in and around the filaments and the dense cores are more complex than simple core rotation or flows into and along the spines. We do see a bit of a trend towards there being some amount of large-scale gradients in the parallel direction. That was what I pointed out with the filaments. But this does also suggest that we have some other behavior that is more dominant in the cores and filaments, perhaps sloshing, collapse, large-scale shears, or some combination of these different kinematic behaviors. And some of the possible contributing factors, especially if we make that assumption that these are very low mass cores that will eventually evolve to being mostly M dwarfs, is that some of these behaviors could come from some mostly dissipated but still underlying turbulence from the initial molecular clouds. And we also need to recognize that parallel and perpendicular gradients may be a bit more relevant in those high mass star forming regions where gravity plays a larger role. So some next steps for me is to compare those filaments in the other tracers in a bit more of a mathematically rigorous way, and also compare the physical parameters of the filaments like the mass and the density. Then I'll also, as I mentioned earlier, I'll be conducting a dendrogram analysis, especially of that multi-component gas in B211, and compare the velocity gradients with other gradients of physical parameters, such as the density. My goal right now is to submit paper 1, which will focus on the filaments and the methodology, hopefully by the end of July or August, and then paper 2, which will focus on the cores, ideally by the end of September. So that is everything I have for you today, and I'm happy to take some questions.
Thank you. Do we have any questions in the room? And for the audience online, if you have questions, please raise your hand or type your questions in the chat.
Thanks. It was a great talk. I was curious about, because from what I've seen, the velocity differences are like a few kilometers per second.
Mm-hmm.
And so when you have filaments that forks, that should, like, let's say that the filament has like a fork and one branch is going faster than the other. Then in the PPV diagram, that should also look like a fork, like in velocity, right?
Yeah.
And like and we should see like a continuous, continuing, rather than if I have like two branches separated, it should be completely separate in velocity. So my question is, the algorithms that you're using, can they separate those kind of forks into different filaments, or do they always see them as the same?
Yeah, that's a good question. So far, it looks like they put them into completely different filaments. So I don't have any filaments that I can really point to where it's clear that there's a branch. But that is also the case in the other filament identification codes that were used in the dust, for example. There are some, I won't try to go look for it, but for example, in the dust, there's some filaments where it goes this way and then suddenly it takes a hard turn to one side. So it doesn't branch. There are some examples in the other tracers where there is a bit more structure, where there are more feeder filaments, as we've been calling them, where there's a main filament that contains cores and is at higher densities, and then some smaller, lower density filaments that connect to it, often at a perpendicular angle. But in this high density gas with ammonia, we don't see that.
Thank you, Lucy. That's a great talk. I have two questions, well, more, but just two. The first one is, for example, here you mentioned that when you identify the filaments, you have like a broken sections or in simulations, when we follow the evolution of the filaments, when you have the core, then the gas around it is being accelerated to the core. So essentially you have like an empty region around, and your filament is broken for a few times. You cannot connect it later.
Yeah.
So I was wondering if you can check if the velocity is particularly higher close to this broken section.
Yeah, I know for sure that in these broken sections, there are some really rapid velocity changes. There are also a few very low density core-like objects that Samantha Chabelli identified in her 1.2 millimeter continuum observations that were also in this general region that weren't identified in the ammonia. But yeah, there's an example actually on this slide.
Right. And the other question is about the core rotation. Can you show the good examples?
Mhm.
Yeah, those ones. Yeah, I was wondering if because well here the gradient like extends like outside the core.
Mhm.
So I was wondering where is here what is the filament in these figures? Because if you have the gradient, the perpendicular is the dominant one. So I was wondering if we are just seeing like accretion from both sides to the filament instead of rotation just in a core.
Mhm.
Since the gradient extends outside. So I was wondering where's the filament here?
Yeah. Yeah, so for these two cores, which are next to each other, the filament is mostly horizontal-ish.
Oh, okay.
So this way, and then for South 37, the filament goes vertical.
Okay,
So with the figure that I showed here, where the parallel gradient was dominant over the perpendicular, especially for those likely rotating cores. My idea was that they were rotating with an axis of rotation that's perpendicular to the filament they reside in.
So when there's rotation, for sure, it's perpendicular.
Not always, since there are these two examples where that doesn't seem to be the case. This one here is a protostar that's fully embedded. So perhaps if we had higher spatial or angular resolution, we might be able to see a core that's rotating with an axis of symmetry perpendicular to the filament. But this one is the only one that's not an embedded protostar and also rotating likely within its filament rather than against it.
Thank you. That's a little better.
I have a question related to the signal to noise ratio you just mentioned earlier. When comparing the different filament regions where we only see dust and some other regions we don't see some of the gas. So in the images you showed, do we observe in the consistent way, or is because we set up the observations at different sub-regions have different sensitivity, for example?
Yeah. So I'll go back to that plot that was comparing the filaments. So each one of these, the CO, the dust, and the ammonia, were all part of three very different surveys with different instruments. So this one, the dust, was part of Herschel. It was done in the infrared with the Herschel Gold Belt survey. The ammonia was taken as a precursor to the Green Bank Ammonia Survey. That was taken with the K-band focal plane array on the Great Telescope, which has roughly 30 arcsecond resolution, and then this processed one went down to 6 arcsecond resolution. And in the map, all of the cores were then observed a little bit more than the rest of the extended structure in the cloud. And then the C18O was with a different radio telescope. So the spatial resolution is a little bit lower than what we have with the ammonia, I think, if I'm remembering correctly. It's a combination of each of these, the two gas and the dust, tracing slightly different environments, but also the surveys all together.
So I guess my follow-up question is, for example, at some regions, like the galactic longitude of 171 degrees, we see that there is a discrepancy between the dust filament and the C18O filament. Is that due to the SNR, or you would think it's actually due to the differences of the gas and dust going different direction?
Probably a little bit of both. Where the C18O is mostly like a little bit more like right along that main overarching structure, where the dust actually truncated a lot of the dust for the purposes of this. So the dust is pretty much everywhere. But for this figure, I only showed the filaments where for the dust where it overlapped with the two gas tracers. So there is more dust, but in part because it has a higher angular resolution than the CO, then you might see more of the little feeder filaments that I mentioned earlier, where a lot of them come in perpendicular and then have some of those central spines down.
All right. Let's thank our speaker again.